वैसे कुछ स्टेप आए थे वहाँ पे, करना था प्ले। अबे यार। ये चाहिए, सिर्फ ये वाला एंगल चाहिए इधर से। बढ़िया बढ़िया। क्या ले गन ही ले ले यार, मेरे से ले ले भाई। स्टेप करो, रहना मेरे पे। अबे यार। हाँ होल्ड इट। रोटेट हो रहा है। प्लांटिंग, ये प्लांटिंग। राइट जा रहे हो ना, मेरे राइट जा रहे हैं। दो है।
Pieces of being a really good software engineer or a good prompt engineer is less about actually knowing the information and more about knowing where to find the information. So, throughout this course, I want you to practice using these resources because they're going to help you be a much
प्लांटिंग के अगेंस्ट यार। अरे बी क्लियर था, काफी टाइम से बी क्लियर था। यार टाइम से बी क्लियर था। यार टाइम से बी क्लियर था।
much stronger developer, much stronger prompt engineer, and just be better at everything that we're going to go over in this course. If Find or ChatGPT gives you a poor answer, be sure to use the GitHub discussions. If you have a question specific to this course, be sure to use the GitHub discussions. Or if you have a more general question about Solidity, about Foundry, or anything like that, you can use one of these resources. Again, I'll go over this more later. But great job. You've done your first bit of prompt engineering. Congratulations. You don't have to understand this section fully. Yeah. You
जैसे सामने मिलेगा। चलो प्लान करो, प्लान करो, प्लान करो। चलो प्लान करो, प्लान करो, प्लान करो।
Now, one thing that we didn't really go over and we kind of glossed over was this memory keyword. And you'll notice if we actually delete this keyword and you try to compile, we'll get an error. Data location must be memory or call data for parameter in function, but none was given. Now, there are actually 6 places you can store data in Solidity. You have the stack, memory, storage, call data, code, and logs. We're not going to go over all of these areas right now, but we are going to go over some of the big ones, which are call data, memory, and storage. And this is going to be it's only going to exist temporarily. It's only going to exist for the duration of the function call. Anytime we call add person with a different name, we can only access this name variable that one time that we call this function. If I call add name Patrick7, and now I try to list of people at 0, obviously we see Patrick at favorite number 7, we can actually never access that Patrick variable ever again because it existed in memory. It existed for a very short period of time, just for that single call. We could also have call data here. Access this name variable that one time that we call this function. If I call add name Patrick7, and now I try to list of people at 0, obviously we see Patrick at favorite number 7, we can actually never access that Patrick variable ever again because it existed in memory. It existed for a very short period of time, just for that single call. We could also have call data here, and we'll go ahead, remove this, deploy the dropdown, and do the same thing. We'll add Patrick, and actually, you don't even need the quotes. Patrick will do 88, add person, we'll see if it's in there. Sure is. Call data and memory both mean temporary variables. Inside of functions, most variables automatically default to memory variables. Strings are a special type in Solidity, so you have to specify memory or call data, and it has to do with the way arrays work in memory, but we'll talk about that much later in the course. Now, the question obviously then follows, okay, well, if call data and memory are both temporary variables, why have 2? What's the difference between these 2? Well, let's try something. Let's have this be a memory variable. And in here, we'll say name equals cat.
अरे यार hold, hold, bro.
I've, so we're going to reassign whatever people put in here to cat. Let's compile this. Looks like it compiles fine. Now let's do call data and try to compile. We get an error. Type error. Type literal string cat is not implicitly convertible to expected type string call data. The difference between memory and call data is that a memory variable can be changed. It can be manipulated. If we pass a memory variable to a function, we can go ahead, memory, and I hit Command S to compile. This is valid solidity. This is not. If you pass a call data variable, you cannot modify it. Call data is temporary variables that cannot be modified. Memory is temporary variables that can be modified. And storage is permanent variables that can be modified. My favorite number was actually implicitly converted to a storage variable since it's added in this state context.
So what he said was that a vending machine is a device implemented in physical hardware that basically implements the conditions of some kind of an agreement. And the conditions of the agreement here are simple. You put $2 in, water comes out. You do not put $2 in, water does not come out. If you do not put $2 in, but water does come out, then that's bad. And the vending machine is basically an encoding of this set of rules, and that also comes with, a mechanism
Outside of a function. If you create a variable that's outside of any function inside of a contract, it'll automatically be a storage variable. And let's delete this line, state context, outside of a function. If you create a variable that's outside of any function inside of a contract, it'll automatically be a storage variable. And let's delete this line. Let's compile. Let's deploy again. Delete this, deploy. We know it's a permanent variable because we can hit retrieve and we can always access what is in favorite number. So if we store 1, 2, 3, we hit store, we can hit retrieve, and we can access 1, 2, 3. So this variable 123 exists outside of function calls. Now, even though I said there are more places like stack, code, log, return, etc., we can only make these variables call data, memory, or storage. And like I said, we'll explain that later in the course. So let's go ahead, let's add this back to memory because that's normally what you'll see. Now, the next question that logically follows is, oh, okay, Patrick, well, why do we need to put memory here, but we don't need to put memory over here? In fact, if we try to put memory there, we get an error. Data location can only be specified for array, struct, or mapping types, but memory was given. Like I was saying earlier, arrays, structs, or mapping are considered special types in Solidity. And the way that memory management works under the hood makes it so that we have to put this memory keyword. uint256 is known as a primitive type, and Solidity is smart enough to know where to put this favorite number always under the hood. Like we were saying earlier, a string is actually an array of bytes, and so as we just saw with the error, we need to put the memory keyword for arrays. So then the next question is, okay, well, what about the storage variable? Can I put that here? No, you can't put that here either. Since this is a function, Solidity is smart enough to at least know that, okay, this is a temporary variable that you're working with. It's got to be memory or call data. It's not going to be storage, since this name is only going to exist for a short duration. So you got to pick one of these other two. So the summary of this section is that structs, mappings, and arrays need to be given this memory keyword. A string is an array of bytes, so it needs this memory or call data keyword. So this code is starting to shape up. It has a lot of functionality here. We can store variables, we can add people, but it has a bit of an issue. If we have this contract and we want to say, oh, what was Kelly's favorite number? Let's say we have 4 people in the array. Let's have Pat, 7, John, 8, Mariah, 10, and Chelsea, 22, or 232. And we ask the question, what was Chelsea's favorite number? Well, the way we would do it is we'd have to actually loop through this list of people to find Chelsea. So we'd say, okay, what's at 0? Okay, that's Pat. That's not Chelsea. What's at 2? That's John. What's at 3? That's Mariah. Or excuse me, what's at 3? That's Chelsea. Favorite number 232. Okay, perfect. I found Chelsea. But obviously, if we had 1,000 people in this array, that would be a very tedious process, and that would take a long time for us to find the person that we wanted. So the question then is there a better data structure than a list or an array to use that makes it much easier to access and find the information about the people that we want? And the answer to this is using a mapping. You can think of a mapping as a dictionary. It's a set of keys with each key returning a special set of information about that key. So it's similar to a dictionary. If you look up the word the word the will have a whole bunch of text associated only with the word the. So let's create a mapping type, and you'll see how it works in practice. So we're going to create a mapping like this with this mapping keyword, and we'll say the key is going to be a string, and it'll point to a uint256. So this is going to be our type. Obviously, what comes after the type, our visibility. So let's just go ahead and do public for this as well. And I like to be very explicit with my naming. So I'm going to say name to number, signifying that this map maps someone's name to their favorite number. And now with this, we have essentially a dictionary where every single name or every single string is going to map to one number. So for example, if we looked up Chelsea, we'd automatically get returned the 232 that we're looking for, instead of having to iterate through this list. So let's add some capabilities to our add person function here so that we can update our mapping. So we have this list of people.push, which adds someone to the array. Let's also update this so it will also add somebody to our mapping. To do that, we'll say name to favorite number, and we put these little brackets in here to specify what the key is, and we'll say underscore name, and we'll assign that to underscore favorite number. What this line is doing is now it's saying, all right, in our mapping up here, in our name to favorite number mapping, anytime you look for that person's name, you'll automatically get their favorite number back. And now you have a much quicker way to access people's favorite numbers just by knowing their name. So let's go ahead. Let's compile this. Let's deploy this. Let's delete our old one. We'll deploy this. Now we have this new name to favorite number blue button. And so let's go through the same problem. So let's say we have Pat 7, John 16, Mariah 32, Chelsea 232. People look up John, we get nothing back. In a mapping, the default value for
बैग में 2 छोटी नोटबुक है वो दे दे
Yeah, put that. Haven't the last one I had.
To use the principles from the first part to design and code a live streaming video app.
Hello everyone, welcome to this system design course. This course is for beginners in a sense that if you have never done system design before, or you have done very little system design, or you have just heard of it or read about it but not got an opportunity to actually do it, this course is right for you. At the end of this course, you'll be able to identify some basic engineering design patterns which are used to design large-scale distributed systems. Let me define each of these terms in detail. Large-scale distributed systems. As the first part of the term says, large scale, meaning that something which is being used a lot or is very intensive in terms of compute or data or any computer engineering principle. For example, Google, let's say Google Maps. This is large scale because A, it has a lot of data. The whole world's map has to be stored inside it. B, it's being used by a lot of people. C, it's being updated very frequently. And D, it has a lot of performance expectations from it. You don't expect Google Maps to go down. You expect Google Maps to return results quickly. You expect it to be accurate, so on and so forth. So it's a very good product being used at a large scale. Distributed systems means that the server or the code that is actually executing this program is not in one place. It's distributed all around the world. So you might have one server in India, one server in the US, one in Japan, for fault tolerance, so that if one of these servers crashes, the rest of the servers can take the load. It's also for performance. If the Indians want a Google Map result, they go and talk to the Indian server because that gives a quick result back. While if they go to the US server, they have to go across continents and then get a response, which is a slow result. Okay, so that's the point of a large-scale distributed system. Many of these companies which provide these solutions expect their engineers to know about system design, to know how to build these large-scale distributed systems. So to do this, their engineering team depends on design patterns, which we mentioned earlier. Design patterns are particular practices, principles, or processes which are used by engineers to build these systems. For example, you have a common problem of a celebrity posting on social media and that post being distributed to a lot of their followers. For example, if Brad Pitt posts something on YouTube and then posts it on LinkedIn, the problem is very similar. It's one piece of content which has to be made into an event and notified to millions of people potentially. And what you want to do is you want to notify them quickly, but you also don't want to put too much load on your service so that the rest of the requests which are coming into it continue being served. This is a common problem. So you extract out a common problem and you solve it using a common solution. This would be a design pattern. Right now, you don't know what design patterns exist, but one popular design pattern for this kind of a problem is a publisher-subscriber model, where Brad Pitt is a publisher and their event is subscribed to by millions of people. An intermediary decides the pace at which you send these notifications, which keeps the server load low and also makes sure that all the notifications actually reach all the subscribers. Now, seeing this, you can tell that as an engineer, you can take a lot of business requirements and convert them into technical solutions. And engineers use system design patterns to make reliable, scalable, and maintainable systems. This helps them convert business requirements into technical solutions. If this sounds exciting to you, watch the rest of the video and you won't be disappointed. Okay, let's start with an example. Let's say that you join a company which does broadcasting of videos to millions of people. This could be Hotstar, it could be YouTube, it could be Zoom also. So some sort of events which are being broadcast to millions of people, and you as an engineer have to devise the solution for this, come up with some technology which can handle this problem. So the first thing that we need to do as engineers is to define these requirements from the user's perspective. And often engineers don't do this. There are product managers in a company which write a product requirement document based on user feedback and data. So that's good to have. You have a well-documented, well-thought, business-backed document, which the engineer can then read and decide on how they can make it happen. Amongst these, you pick up the most important features first. Taking the example of a live streaming system, users who tune into your system should be able to watch the stream live. Whether you see it at HD quality or you see it at 480p, that's probably a secondary issue, but being able to see the video is a primary issue. So for that, you have to make sure that your server doesn't go down, and you have to also make sure that your bandwidth requirements are sufficient. Second, you reduce these features to data definitions. So one of the features which might be defined is users should be able to like a video or should be able to like a comment. What you then do is you look at the concept of a like, the abstract concept of somebody liking something. What does that mean? It means that a particular user likes a particular comment. Okay, so it has a like ID, it has a user ID who's done this, it has a timestamp, when was this video liked or when was this comment liked. The comment itself is an abstract concept. It's probably going to be mapped into an object. It has an ID, it has a user who has typed this comment, it has a creation time, and maybe it also has a thread in which it was posted. So you're seeing that I'm taking features, or I'm taking these abstract concepts from the product requirement document and converting them into data definitions, which are useful for an engineer. These definitions can then be mapped into objects, which can then be mapped into the database. Once you've defined the data that you need to store, you need to define endpoints through which this data can be manipulated or queried. So I want to read comments. Give me an API, an HTTP API, FTP API for all we care, The network protocol at this point is not important, but some method by which I can send an electronic signal from one place to our server, and our server can respond to that signal with the data that they need. So our server is now encapsulating this data as per the user requirement and defining some endpoints which are called APIs so that external users can
पानी की बोतल देना.
query and manipulate our data. We do this for every feature that we have, core features and also optional or good to have features. Usually a product requirement document does not define optional or good to have features. These are all core features which are required in the document. The good to have features will be probably picked up in the next document. So you don't need to think of which features are optional, but you do think of which features are most important as an engineer. The second thing is you also have certain engineering requirements when you're creating these designs or coming up with some code. You want to make sure that none of your services fail if there is an outage. So for example, if you have an outage in India and your comment service is in India, then you don't want the entire system to collapse. We talked about this a little earlier, that you have multiple servers spread across the world to avoid a single point of failure. You may also have multiple servers in India itself. So if one Indian server fails, another one picks up its responsibility. So here you might have some sort of data duplication because of which the other server is quickly able to pick up the responsibility. Or you have some sort of partitioning that 50% of the users are going to this server, 50% of the users are going to another server. So just 50% of the users are affected. Another common and often missed out engineering requirement is extensibility, which means it's not just about the technical solution that you come up with, but also how easy it is to change that solution. For example, if you write code to send a message to millions of users, and you need to make a small tweak to that code because now you don't want to just send it to 1 million users, you also want to check whether they have read those messages. So a read receipt. The problem with writing code which is highly coupled with the feature is that whenever there's a changing requirement, you have to put in a lot of effort to redesign, test, and actually deploy that code again. So you want your features, your engineering features, to be extensible. For this, you have to take out your engineering crystal ball and gaze deeply into it. Actually, what you do is, as an experienced engineer especially, you look back at your past projects, you look back at things that you have done, you look back at things that people have done, what the world is doing. And based on that combined knowledge, you build a system so that you can reasonably expect it to scale and extend as requirements change and as more and more users join you. Finally, this design needs to be tested. This is an important part of system design, which is not really thought through in interviews. But in the real world, when you have a system which is designed by, let's say, a senior engineer, that design has to be tested. So you run through a couple of requests with edge cases, with common cases, and you see whether these requests are having a sensible flow in the system at a high level. The other thing that you can do is you can use sophisticated tools to load test this design. You can have some sort of capacity estimation to actually see whether this design is feasible. But importantly, you have to test this design before you start getting into the code. Okay, let's recap with an example. Let's say we have a live streaming system. How would we go about designing this? Requirements would be streaming video, processing video, sending video to multiple customers, so that is broadcasting. Not failing is a requirement. Showing advertisements, allowing reactions, showing disclaimers or news flashes, having graceful degradation of video quality in case you have low bandwidth, allowing multiple device support, and so on. Amongst these, you'll see that the product requirements are mainly showing video to a lot of users. That's a major requirement. And also, of course, comments is a thing and being able to react is a thing. You may also consider product requirements to be showing a banner in case there's a problem. It is. But the core requirement, of course, is just showing a video. So I'll pick this feature first. This means that I have to capture video from a source, let's say, which is shooting at 8K. And I should be able to store it in some place in my server so that I can query it later. In a live streaming system, the later part, the query it later, is probably milliseconds. So I may not want to query that data at all. I may want to directly stream it from the video camera onto millions of people. Taking a step back, it looks impractical because if I'm shooting at 8K at very high quality, and this is raw footage, sending that much data to people on their mobile phones is unreasonable. So yes, I'll need to store it in some sort of a database or a file system, and then I should be able to stream that or query that out so that I can distribute it to all of my customers. But I don't want my customers to know exactly how I'm doing this, or I don't want them to know about there's a change in implementation tomorrow. I want this to be a black box so that they can pay me and relax. They just hit an API and their problem is solved. Of course, I might give them clients which are downloadable on the App Store, which take care of all of this API and querying also, so that as end users, they can just enjoy watching an event instead of thinking about how the technical part of this is actually happening. These APIs have well-defined signatures. You can tell that if I want this video ID in a particular format, then I have to query a particular API called getVideo, which is going to be returning me objects of type frames, and those frames are also well-defined. So if you have ever written a program, you know that these API signatures are very similar to method signatures. The only difference being that these APIs might be queried not through a programming language, but through a network protocol like gRPC, HTTP, FTP, any kind of protocol which defines exactly how an electronic message is going to be taken from one place and sent to another. And also how the response is going to come back and how the behavior of this interaction is going to be. That is defined by the protocol. So this is great. We have a system which is storing some data, which is valuable to us because we want to watch this event live. And this data is going to be queried using APIs. Also, these APIs are going to be tested beforehand so that the clients who are using this, who are paying for this service, are not disappointed when they actually query it. As engineers, we have to think of various failure scenarios. What if the database which is storing your videos crashes? What if a particular firewall on the internet starts blocking all of your requests? What if one of the services that you have written in your entire system, one program, one piece of code, starts misbehaving because you have introduced a bug in it, or there is somebody who has maliciously entered the system and changed the code in that system? We'll have to use some design principles that we talked about earlier. This challenge may also be a feature request. Like if you want the musician who's playing in this live event to be able to talk to their audience, do a back and forth with some audience members who they select either randomly or based on their activity. So you have to display those users to this musician live and be able to broadcast to parties to millions of people out there. So taking these requirements, let's try to design a live streaming application. So there's two ways to approach this. One is from customers or our clients to our server, which is out there in different parts of the world, and then to our database, which may be, again, in different parts of the world. That's one way to think. And the other way to think is from our database to our server. So what kind of data do I need to store to enable my server? And what kind of APIs do I need to expose to enable my customers to be able to use my product? Okay. Both of these approaches are fine. They require different ways of thinking though. When it comes to a data-based approach, you will need to consider what kind of data do you need to store. And often you'll be thinking of these pieces of data as tables. So you need to store a video with an ID. The video has a name, it has a size, and it has some data. That's one way to think. I prefer the other approach where customers define their problems, which are then fulfilled using APIs on the server, which are then fulfilled by storing some sort of data in the server, in the database. And that data is then mapped onto tables, like so. And so for this system, this is the approach that we'll be using. Okay, in our case, customers are live streaming customers. So they may be streaming from their cell phones or laptops or the TV. And we can't assume which device is being used more often. In certain countries, you'll have certain devices being used more. There could also be a tablet, of course, from which they're streaming this video. But you see that there are multiple devices which need to be catered to. This is a front-end UI design problem. System design is more to do with the distributed systems back-end part of things. There is some system design involved when it comes to API interactions and how to store or cache data on the front end, but that is not what we are focusing on here. We are focusing on the back-end part of the system. Okay, so these clients need to be able to query our server in real time. So what does our server need to have? Its APIs are going to be something like get video, and you pass in the video ID, and you pass in your device type. So I send you the resolution based on your device type, and you might have a particular offset that, I've already seen the first 10 minutes of the video. Show me everything after the 10th minute. If I have a video API like this, I also need to return something. So the return type could be some frames, some video frames. Let's say each of these frames is 10 seconds long. So a single frame is what I send back, such that it is of this video for this device and after 10 minutes. So 10 minutes to 10 minutes and 10 seconds, that frame is picked up and sent to the client. If you know about API design, you see that this API is not well named. Get video means you get an entire video, but you're returning a frame. So maybe we can rename this to get video frame. Another thing is, if you're using a REST protocol, get is going to be defined in the request itself. So GET over here is going to say that get me video is enough to say that you want a video. In our case, like we said, it's a frame. So maybe get frame or get video frame is what we are looking at. You'll notice that Vimeo also has a similar API when it comes to getting the next 10 seconds. YouTube also has an API which tells you from which point to which point do you want to see the video. So I'll give you all those frames. Great, so we have this. What else? You should be able to comment on a video, okay? So what you should be able to do is you should be able to post a comment. Again, I'm using a well-known concept in REST. Post means you want to put something in the server. You want to manipulate some data, you want to add some data to the server. So if I say post a comment with an ID, here I don't care about which device it is coming from, because the comment is just data which has to be persisted in the server. Based on that, I'm not going to be changing my response or changing the behavior in which I'm posting the comment. So I don't need that. I don't need an offset, but I do need the comment data. I need the author of the comment. I need the post on which this comment. Also has a thread in which it was. You have to test this design before